So let us see today module 4 part 1, which deals with two main parts: wavelength division multiplexing, WDM. WDM means wavelength division multiplexing, concepts and components, and optical amplifiers. WDM means it is similar to FDM and TDM, what we know about it. Okay, so today we can see the concept of this wavelength division multiplexing. So how it is similar to FDM and TDM, and how it is so unique with respect to optical fibers. So let us see in the next slide the concept of wavelength division multiplexing. So normally you will get the question like define WDM and explain briefly from 3 to 4 or maybe up to maximum 5 marks. So how we can define? It is a concept or technology of combining more than one independent wavelength. So means each wavelength is uniquely different, and each wavelength is carrying a differently formatted data. Okay, so technology which is combining more than one such wavelengths, unique wavelengths carrying differently formatted data is called wavelength division multiplexing. So this is the definition. Then next, how we can explain? You can explain with respect to 2 points here. The first point, what I am indicating, how WDM is evolved, who is main responsible for the evolution of this WDM, and how it is going to make WDM different from the point-to-point links. See, in 1980, point-to-point connections were deployed, which is able to carry only single wavelength, only one wavelength, not more than one wavelength. But with the development of high quality light sources, okay, coherent light sources, we can say, like lasers, okay, so like that, which are able to generate light, single ray of light with unique wavelength, and that too you can see the wavelength is very much reduced in terms of less than even 1 nanometer. So this is the main reason, or you can say the source of evolution for this concept or technology WDM. Okay, so how it is different from the point to point? In point to point we can transmit only single wavelength, but in WDM we are able to transmit more than one wavelength. That's how we can explain. So this is the one point we can include in the elaboration of this WDM after definition. So another one, because of this only, in connection with this, so what we are getting, the data carrying capacity. You can see if each wavelength, if you think of carrying it or supporting 10 Gbps, and if you are transmitting 10 overlapped or multiplexed different wavelengths, each one supporting 10 Gbps means 1 Tbps data rate you are able to support, data transmission rate. So that is another advantage. So means that its main feature is like this. So how we can say each wavelength is going to support differently formatted data. For example, wavelength 1 may support for music, wavelength 2 may support for speech, wavelength 3 may support for your data, like that up to n wavelengths. So these are the two important points you have to include when you are going to explain about WDM. That is very much important. So how we can think about this? Define the WDM. Okay, the next we can elaborate it. The first point is its evolution responsible. Who is responsible for evolution? The advent of that coherent light sources like lasers, and how it is going to make your WDM different from point to point links. And second point is its increased data handling capacity, data rate capacity, data transmission capacity, that with differently formatted data signals. Okay, so these are the 2 points you have to include when you are going to explain about wavelength division multiplexing. So next, let us see the operating principles of this WDM. Operating principle means how we can implement this instrumentation point of view, how we can see this one, wavelength division multiplexing. Okay, so mainly you can see its main functions are like this. we need to separate, we need to combine the things, because we are able to now we are able to transmit more than one wavelength. We need to combine them. We need multiplexer for this one on transmitter side, and on the contrary, on the receiver side, we need to distribute them. We need demultiplexer is required at the receiver side. Then isolation and amplifiers are required. We need to isolate without overlapping between these wavelengths, and amplifiers all the way are required from transmitter to receiver. It is required. So to support these functions, combine, distribute, isolate, and amplify, so we need two important devices here. The passive devices which will help us in combining or distributing, like circulators or isolators, which are passive devices, which will not require any external power supply. So therefore we do not have such kind of flexibility or control over the operation of such passive devices, but we can use for such functions. Another one, the active devices, like tuned optical filters, which are actually based on the wavelength at which we are going to operate. Okay, so these are the devices which are useful in the implementation or the operating principle of the WDM. Let us see how it is going to operate. So if you look at this one, on the left hand side we got independently modulated light sources here in the left hand side. Okay, so there you can see different transmitters are there. Transmitters are nothing but tunable sources. Each optical source is tuned to different wavelength, generating different wavelength optical rays. Then multiplexer, wavelength multiplexer is going to combine all these things, lambda 1 plus lambda 2, without any overlap. And on the receiver side you can see demultiplexer is there, and it is going to distribute them, demultiplex them, all these individual lambda 1 to lambda n wavelengths with respective receivers, which are there consisting of optical filters. So these optical filters, we need to have a very sharp cutoff frequency. Very sharp cutoff frequency is required in order to, or wavelength is required in order to overlap between these things, so that the lambda n receiver should recognize only lambda n, not lambda n minus 1 or lambda 2 like that. Or lambda 2 receiver should recognize only lambda 2 wavelength, not lambda 1 or any other wavelength like that. And moreover, the overlapping, we are thinking the cross stacking, we can say cross stacking, nothing but overlapping between the, that is allowed up to minus 30 dB. Okay, so overlapping between wavelengths is nothing but to some extent we can call it as technically as a crosstalk, that can be allowed up to minus 30 dB. So sometimes you might have experienced that if two people are talking, you will sometimes hear the third person is will listen sometimes. That is called a cross talking. So that can be allowed up to minus 30 decibels. So these are the two first parts you need to explain, and then remaining between, you can see pre and post amplifiers are there. Let us see how to explain them. Okay, so here you can see post amplifier. Post means it is located at the, it is the first amplifier which is going to receive the output of the multiplexed signal, multiplexed wavelength signals, lambda 2, lambda n, whatever the signals are combined. So that signal is first received by this amplifier, which is located at the output of the wavelength division multiplexer. And its main function is, we know that amplifier, what it will do, if any signal is weak, it will amplify it. Similarly, that's why it is called post amplifier. It will be located at the output of the multiplexer. Pre-amplifier is, it is called pre means because it is the first signal which is going to receive the combined signal. That's what is called pre-amplifier. And inline amplifier is nothing but amplifier which is residing in the repeaters. You can see here the total length of optical fiber spanning from post to pre-amplifier, that is called span. This normally in terms of kilometers, consisting of repeaters. So repeater, we need amplifier because it needs to amplify the weak signals or distorted signals which have traveled some distance, then again repeater will retransmit it to next repeater, like that. Okay, so in all the cases you can see based on their location and application they got their names. Post amplifier at the output of multiplexer, pre-amplifier at the input of demultiplexer, inline amplifier means it is residing in line with this optical fiber cable, means it is residing in the repeat, that is the meaning. Okay, so this is how we can explain about wavelength division multiplexing, implementation of that one. Okay, so far we have seen how to define WDM. Okay, how to define WDM, how to elaborate it, and its implementation we have seen. Okay, so in context with this, just I will want to bring to your notice that three important bands of the WDM. O band, which is operating around 1300 to 1550 nanometers, operating over 14 terahertz. Second one, S or U band, operating over 15 terahertz, over 1500 nanometers. And this one is the another one, the third one, the standard designated by the ITUT. ITUT means International Telecommunication Union for Telephone. Its main job is to assign the wavelength based on the application. Suppose if you want certain range of wavelength or frequency spectrum for your specific application, then it can be allocated by ITUT. So the standard name is G.692, that you can see later when you are going to study about WDM standards separately. So these three bands we have to keep in mind along with the values. Okay, so which is useful in solving the problems, because sometimes the graph may be given, or most of the times graph is not there in the exam. So here just shown the formula here, the giving the relationship between the velocity of light in a vacuum with the wavelength and band. Okay, wavelength band, difference in the wavelength band. So some of these values we are getting from the graph here. 14 terahertz, it will correspond to how much wavelength difference. 15 terahertz corresponds to how much wavelength difference. Here you can see 100 gigahertz corresponds to 0.8 nanometer, like that. So you have to remember these dimensions here. O band means this much, yes, U band means this much, ITUT band means this much range. So if you see here, on the graph I just written here, delta V 14 terahertz corresponds to a spectral band of 100 nanometers. That is the meaning. That's all. Because sometimes if the graph is not given, you have to remember the values. That is useful. That is quite useful in solving sometimes the numericals. Let us see the WDM standards here. So we'll start its explanation in comparison with FDM. In FDM, what we mean by FDM? It is the allocation of different frequency bands, range of frequencies to different bands. Okay. The similar way we are going to allocate different wavelengths. Okay, that is a wavelength division multiplexing as per the specification of ITU. That is called frequency spacing between different wavelengths. That is important. So the first standard which is actually proposed by ITUT is G.692, which ranges from 193.1 terahertz to 100 gigahertz, 100 gigahertz to 193.1 terahertz. The nanometers ranging from 1550 to 1552.52 nanometers. That is the range. Another alternative approach will be 50 to 200 gigahertz with the spectral bandwidth corresponding to 0.4 to 1.6 nanometers. So these standards means you have to remember the dimensions here. So this is how you have to initiate the explanation of this WDM standards. So many times it has been asked in the exam, write a short note on WDM standards. So you have to be like that, you have to start its explanation. Then we can continue this discussion with the two modalities. Two versions are there in WDM. One is a dense wavelength division multiplexing. Its main features are going to be G.692 standard. Compared to the previous one, it is going to follow G.694.1 standard. Okay, applicable to S and L bands, and its applications are encompassing to MAN and WAN services. These are the frequency ranges and wavelength ranges. So these are the main dimensions here. So DWDM standard name it is going to obey is G.694.1 over S and L bands, and frequency spacing is ranging from 100 to 12.5 GHz with a spectral band of 0.8 to 0.1 nanometer at 1550 nanometers. So this can be supported with a temperature controlled coherent laser diode sources. Temperature is controlled because heat is generated. Because of that, temperature control is required. Now to generate coherent light sources with unique wavelength, heat is generated. And more stable such diode sources or optical sources are required. So the main feature you remember, it is operating over the SC and L bands. Its frequency ranges you remember, and it needs the temperature controlled laser devices and applicable to MAN and WAN services. 4 points. SC and L bands, stable temperature controlled laser diodes are required, MAN and WAN services, and these dimensions. 4 points you have to remember, because in next version in CWDM we need to compare it with these 4 points. Okay, so I may not come back to this slide, but you have to remember with these 4 points we have to compare there. So next we can continue with small block. This WDM you can see here, very much clear that lambda 1 you can see coming from channel 1 separately, which is carrying video type of data. Lambda 2 is coming from channel 2, which is accepting audio kind of data. So you can see here channel 3 it is giving lambda 3 with text supported data. Like that, all such n wavelengths are carrying differently formatted data. That is a very important feature of this WDM technology. Later they combined by DWDM multiplexer, remember. Then here we will come across the amplifiers, as I already explained, post amplifier, inline amplifiers, and here we will get pre-amplifiers, demultiplexer, the sharp cutoff wavelengths for the optical filters. Distribution is happening here, like that. So this is what DWDM you can explain. So normally one thing you want to mention in your explanation when you are explaining its block diagram DWDM is EDFA is used. EDFA amplifiers, doped fiber amplifiers, erbium doped fiber amplifiers is used for long haul application. Long haul application means the length of this optical fiber what you are observing spanning over very large distance, in terms of thousands and thousands of kilometers. It is very long haul. Long haul is larger than long. That is the meaning. That's all. Okay. Let us see another version of